This is the first video in a series of videos about buffers, pretty math-heavy portion of the acid-base chapter. We are going to start out with a discussion of what is a buffer, what is its composition. Then we're going to talk about what happens when you disturb a buffer with a strong acid or base. And we'll end with a new tool, the Henderson-Hasselbalch equation, that will help us to do buffer problems. So starting out with a buffer composition, you've probably heard of this before. They're used in biology as well. So we use buffers because they resist small changes in pH. Buffers are especially useful in biological fields or biochemistry fields where you're trying to study enzymes or other bacteria that live at a particular temperature or in a particular place, like your body, that has a certain pH. So we can keep that pH relatively the same by using a buffer. And what we need to do to keep the pH from changing is we need to be able to resist the addition of strong acid and to resist the addition of strong base. So our buffer needs to have two parts, one to do each of those two jobs. So our first part is going to be a weak acid, because weak acids neutralize strong bases. Acid, okay? And then our second part is going to be a weak base. Because weak bases neutralize strong acids. So our buffer is going to be like the superhero, and our two supervillains are hydroxide and hydronium. And we have to try and find a way to thwart our two supervillains to make sure that we save the pH of the system. So we have this acid and we have this base, and they're each doing their own job, but we also need to make sure that they don't neutralize each other, because if the acid and base neutralize each other, then we have nothing, there is no superhero anymore. So to do that, we're going to be sneaky, and we are going to choose a conjugate pair. Conjugate acid-base pair, like ammonia and ammonium, because these won't neutralize each other, they will push the equation back and forth. So we're going to choose a conjugate pair. So this is about the what that makes up our buffer, and we also need to know about the how much. So here's a new term called the buffer range. So the amount of buffer that we add needs to, the ratio of the two pieces needs to fit within these two limits. So the amount of the weak acid and the weak base that we add, the ratio of the two needs to be between 10 and 1/10. And so if you remember that the pH scale is a logarithmic scale, log base 10. This is one pH unit and another pH unit. So we can buffer the pKa plus 1 to the pKa minus 1. That is the range of a buffer. It can buffer in one pH unit in either direction. And we have another term, and that term is buffer capacity. And the buffer capacity is about how concentrated the supervillain has to be to defeat it. So the best possible buffer has approximately equal amounts of the weak acid and the weak base. So that it can resist equally well in both directions, acidic and basic. And we also want to have a relatively large amount of each. We want to have a concentrated buffer. The more concentrated our buffer components are, the more moles of strong acid and strong base we can resist. Okay, those are the basics. That's how to make a superhero, how to make a buffer. So now let's talk about what happens in the epic superhero supervillain battle. What happens when we disturb a buffer by adding a strong element to it? So we're going to do this in terms of a bar graph. Let's see. So in the best of times, we have a buffer and it's made up of approximately equal amounts of our weak acid and our weak base. So these bars are supposed to represent how much of each of these we have. When disaster strikes, a strong acid is added, an H3O+. And so something is going to happen to this buffer to resist the pH change. So the weapon that we're going to use to fight strong acid is going to be base. Base and acid neutralize each other. So when disaster strikes, our weak acid, A-, neutralizes our strong acid, H3O+. And so how does that affect our bar graph? Well, if we're using the weak acid to neutralize H3O+, that bar is going to decrease in height. And when we use up an A-, it neutralizes to form the other half of that conjugate pair, the HA. So that bar is going to get taller. So we use up some of our weak base. Oh no, this should say weak base. There we go. We're going to use up some of that weak base and we're going to increase the amount of our weak acid when we react with a strong acid. Okay, let's look at the other case. If we fight our other supervillain, strong base, hydroxide, the opposite is going to happen. When we have a strong base added, it is going to be neutralized by the weak acid HA. So our weak acid HA neutralizes our strong base, hydroxide. We'll underline that for dramatic effect. All right, so our weak acid reacts with a strong base. When the weak acid reacts, it disappears. So its bar graph gets shorter. And as the weak acid is used up, it is used to make its conjugate pair, weak base. So that bar gets taller. So our HA bar got shorter. We used it up for the neutralization, and our A- bar got a little taller as it was formed by the process. So when the going gets tough out there and there's a lot of math going on and there's an awful lot of ice tables, I want you to return to this picture. When we add a strong acid to a buffer, it's neutralized by the weak base. When we add a strong base to a buffer, it's neutralized by the weak acid. Okay, so that's our qualitative description. And now we need to do a quantitative description of how much weak base or weak acid is used up. So when we talked about weak acids and bases, we used an ice table. And now that we're moving into disturbing a buffer system, we're going to use a DNA table. We use DNA tables to neutralize strong acids and bases. If you're reading in your book, this is called a stoichiometry table. Okay, so let's look at each of those situations we talked about before with each of our two supervillains and look at how much this is going to change. So this table is going to use moles as the unit. And our acronym is going to be DNA. It's going to stand for disturb, neutralize, and after. And when we write the equation across the top, this is no longer an ionization. It's not just one weak piece in water. This is a neutralization. So we're going to use a neutralization chemical equation at the top. So over here, we're neutralizing that weak base. So we're going to say our weak base, which neutralizes that strong acid, H3O+, is going to form conjugate acid and water. So we're going to set up this table in a similar way. There we go. And then I'm going to add in some numbers so that we can look at how this table works without actually doing a math problem. So when we have a buffer, ideally, we have approximately equal amounts of the weak acid and the weak base. So let's just say we have 2 moles of weak base and 2 moles of weak acid, ideally. And this is liquid water, and we always ignore liquid water. So the first line is for disturb. You disturb a buffer by adding in one of those supervillains. In this case, we added in a strong acid. So let's say we added in 0.5 moles of strong acid. So the second line is for neutralize. Neutralize means we're going to use up all of this piece, because strong acids and bases go all the way to completion. So we use an arrow that goes all the way to the right. So what we're going to do is we're going to subtract out that entire strong acid, just like we did the first time we looked at strong acids. We'll subtract out that number from all the reactants, and we'll add it to all of the product. And then for the after line, it's the sum. We'll add down. So 2 minus 0.5 is 1.5. 0.5 minus 0.5 is 0. And 2 plus 0.5 is 2.5. So if you're buffering and you're in the buffer region, you're going to neutralize your strong acid all the way down to 0. That's how you know that you've done your DNA table correctly, at least for a buffer. Okay, and let's do our other supervillain, hydroxide. We'll make another DNA table with moles. And for hydroxide, our weak acid is the one that's doing the neutralizing. So we've got weak acid that neutralizes hydroxide. And after it's neutralized, HA forms its conjugate base, A-, and water. So it's essential that you get the correct equation written across the top here. All right, so let's say we have that same buffer system. We have 2 moles each of our weak acid and weak base, about the same amount. And then let's say we disturb it with 1/2 mole of strong base. And we don't include water. So D is for disturb with that strong part. N is for neutralize. So we use up all of our strong part if possible. And I don't know why I'm writing the units in every little box because they barely fit. 2 minus 0.5 is 1 after. 0.5 minus 0.5 is 0 after. And 2 plus 0.5 is 2.5 after. So after we neutralized our strong base, there is 0 of it left, and our arrow goes all the way to the right for that strong piece. So in the interest of full disclosure, you should know that ice tables are a real thing that really do exist. And if you look them up on the internet, or if you look them up in your book, you will be able to find it in the index. But the DNA table is a name that I completely made up myself. It's usually called a stoichiometry table in the textbook, but I think that a good table deserves a good acronym. However, I don't want you to mix up the DNA and the ice table, so I'm going to make a quick analysis, compare and contrast, so you can remember which one is which. So the DNA table is the new one that we just added. And we wrote the neutralization reaction across the top. We add an acid and a base together on the reactant side. When we wrote the table, all of our values in the tables were in moles. So that's another difference. And the third difference, the reason that we use the DNA table is we wanted to use up all of the strong acid or base if possible. You'll see when we get to titration problems that at some point, if you add enough strong acid or base, you are no longer in the buffer region and you won't be able to use it all up. But if you do in fact have a working buffer within the buffer region, you will use up all of it. Okay, and so remember our ice tables that we used for weak acids and bases were a little bit different. The reaction across the top, that was the ionization reaction. That was a weak acid or base in water forming ions. The values in our table had different units. We usually used units of molarity, moles per liter, or units of pressure, usually in atmospheres, because these are the values that have to be plugged into the K expression at the end. And the purpose of our ice table was to dissociate a weak acid or base so that we can find the pH in the solution. So we use the DNA table only for buffers when there's a neutralization of a strong acid or base. We use the ice table anytime we have a weak acid or base and we want to look at what its pH is in solution. So here's your handy guide of when you need to use these tables. To calculate the pH of a buffer solution, only for buffers, only in their buffer range. We will always need an ice table. Oh, getting carried away there. An ice table. There we go. So whatever we're doing, we will always need an ice table. Additionally, if the system is disturbed, we added that supervillain, we added a strong acid or base to it. Disturbed with a strong acid or strong base. Then we will also need a DNA table. Looks like I should have underlined this one in green. Oh well. That one's in green and that one is in red. So ice tables are for any time you have a weak acid or base doing anything in solution. And when you have a disturbance from a strong acid or base, you will also need to use a DNA table. So in the next video, we're going to do an example problem, an example buffer problem using DNA tables and ice tables, so you can see how they work.